Welcome everyone. I'm glad you could all make it. Okay, so we have this wonderful figure that was made for the conference. Illustrates all the things that we would like to be able to explain. And on the right is a dark matter tree is something that I sketched in the mid-90s when we used transparencies. So that's a scan of the transparency. So that's all freehand art. I used to be able to do that. And basically it was my attempt to try to organize my thinking about this with all the sort of the evidence that drove the need for what we generically call dark matter, which are dangerous words because just saying dark matter just means there's some invisible mass, and that can mean literally an infinite number of things. Whereas in the standard ΛCDM model, we mean something more specific, and there are different flavors of that. So we have to be careful what we mean by dark matter. And of course, more generally, as we're here to discuss, it might be that it's not dark matter at all, that we have the equation wrong, and that we only infer the presence of invisible mass because of there's some more general equation that we should be using. And so there are all these ideas up at the top, sort of the fruits of the trees that grow out of the roots, the empirical roots of the problem. And as an observer, I've always viewed it as my job to try to trim back the tree, falsify these ideas one at a time, and then whatever survives is the right answer. Having done this for a quarter century, I would say this is more like a weed, because every time you trim something back, it just springs back up again. So for example, strange nuggets was an idea in the mid-80s that did not survive very long. It's come back. It's a form of macros. Basically, it's the same thing come up again. And that happens over and over again. And I would argue that most of this tree has all been cut down, and it keeps growing back. And I think we should be arguing about whether MOND is better interpreted as a modification of gravity or something to do with inertia. Thus, to my mind, it's the only interesting question left on this tree, but that's not where most of the community is. So, I want to sort of attempt in the time allotted to address two basic things. I want to cover the data, what I think are the essential aspects of that, and also talk about the scientific method. So the data can be summarized by these sort of relations, which I think are tantamount to natural laws in the same sense as Kepler's laws for galaxies, or natural laws for Kepler's laws for planets. These are natural laws for galaxies. And they all come down to the presence of this acceleration constant in the data. So this is the amplitude of the mass discrepancy, how much dark matter you infer in systems as a function of the acceleration scale. You are here, right? This is what we feel standing on the surface of the Earth. And there's binary pulsars that can go up to very high, emerging black holes through the solar system. And it's only at these very low accelerations that you start to see discrepancy. And it sets in a bit sooner for clusters of galaxies than for galaxies individually, but it's all the action is down there. Okay, so of course flat rotation curves, this is what launched the modern era of the missing mass problem, or as I think it was Bekenstein suggested, that it should be called the acceleration discrepancy. It's a more general term than dark matter. And so this has been with us for half a century now, but it's not just that. If you talk to cosmologists who come out of the particle physics background, they know rotation curves are flat, and therefore we need dark matter, and they're off with running with whatever dark matter ideas they have. And those ideas generally are not informed by these other things that they should be. One of which is Fisher, that it's not just that rotation curves are flat, but that amplitude of that flatness depends on the amount of mass that you can see. Big galaxies rotate fast, small galaxies rotate slowly. And that's extremely ordinary. So here's the Fisher relation. Basically, the luminosity or stellar mass here correlates with that. And that's good for bright galaxies. There's the Milky Way in there. But as you go to lower and lower masses, then things sort of break down, as entirely due to the fact that most of these low mass galaxies that are rotating are very gas rich. And so you need the entire mass in that mass budget, both the stars and gas, and then you reestablish a good correlation over that. Note that I said entire mass, as Bob already alluded to. That's just the baryonic mass. Nothing about dark matter on this problem. Now you also notice I grayed out some points. Those are points with errors larger than 20%. And I only do that to show that there are always outliers. You always find people saying, oh, what about DF2 or something like that? It's off of this relation and therefore MOND is falsified. That's astronomy for you. There are always outliers. The forest is that correlation. The rest are trees. Okay? I don't care about the trees until we understand the forest. Now, there's more to it than that. Here are two galaxies, UGC 128 and NGC 2403, that are indistinguishable in that Pauli-Fisher plane. They have the same baryonic mass, the same flat rotation velocity within the errors, but very different rotation curves and very different mass distributions. So it's not just Pauli-Fisher, but the dynamics knows about the distribution of light. The high surface brightness galaxy has a rapidly rising rotation curve. The low surface brightness galaxy has a slowly rising rotation curve, more or less as you would expect from Newton. But you don't expect them to fall in the same Pauli-Fisher relation. And if you normalize the radius by the scale length of the disk, then they're practically indistinguishable, right? So whatever is going on knows about the distribution of light, not just the total mass. And a lot of dark matter theories predict that it should just be the radius, right? A generic NFW halo from a dark matter only simulation at the same mass, has the same structure, so galaxies of the same mass should have the same rotation curve. It's the same dark matter component of the rotation curve. Okay, so that's why people these days complain about diversity, that geez, this is a lower number than that number. That's surprising. That is surprising in terms of dark matter. Okay? But that's only half the story. If you normalize by the scale length, then it's the same rotation curve. That goes unexplained because in the dark matter theory, you shouldn't know anything about the scale length of the light. No reason for that. And this maps into what I've been calling the central density relation, which basically compares the dynamical surface density at the center, which has to do with the rate of rise of the rotation curve. So here's the gradient that comes in here in a formula that goes back to Tumori 1963, which I love to quote because it's older than I am. And Federico Lilly worked this out. And that correlates with the central surface brightness. See a nice correlation there. That solid line is just 1-to-1. So if all we had was Newton and no dark matter or other business, everything would be along there. And that's true for high surface brightness galaxies. You don't need dark matter in the centers of those. But you can see these two galaxies I called out segregate here, even though they're indistinguishable in the Pauli-Fisher plane. The high surface brightness galaxy has a higher surface density than the low surface brightness galaxy. Also notice that at low surface brightness, you have a discrepancy. This is what attracted my attention to the problem in the first place, as I was working on low surface brightness galaxies, and these things had discrepancies even in the centers of the galaxies, and that was very surprising at the time. So as Bob also mentioned, there's what those of us who knew Renzo Sanchisi call Renzo's rule. And really, I think this is another law of nature's, that basically when you see a feature in the light, you see a corresponding feature in the rotation curve. So for example, this galaxy has a very small bulge, but it's very centrally concentrated. And that has a corresponding feature in the rotation curve. That happens in the Newtonian regime, so you can say in dark matter that's just all bulge, and so you don't care. But you also notice it, and this is the case Bob already showed, in GC 1560, where there is a broad feature here due to asymmetry in the gas distribution, and that is reflected in the total rotation curve. And this is a huge problem for any standard interpretation in terms of dark matter, because the discrepancy is large. That means it's completely dark matter dominated, and there's no reason whatsoever why a spherical dark matter halo should have that same shape imprinted on it that you see in the baryons. The baryonic tail is wagging the dark matter dog. Now, so you ask people about it, they say, oh, well, it's out of equilibrium. Okay, it's a chance equal thing, so you can always say that. But it doesn't make sense. And Renzo had noticed during the course of his career that this happened over and over and over again. And in fact, he said this to me in 1995. When I was working on most of his writing Galaxies and visiting Groningen, and we had this hammer and tongs argument about it because it didn't make sense to me that you could have this large discrepancy and also see these features. So you see that 2004 is when he wrote it down because he spent the time going back and checking that this actually applied to LSPs as well as high-surface brightness galaxies. And it does. And that's the thing that's confusing. Okay, there's the radial acceleration relation. You can show rotation curves as v against r, but that you can also work into the centripetal accelerations. You can plot that against what's predicted by Newton, so it's basically comparing the data to that blue line, which is what would happen if there's no dark matter or MOND or anything else. And when you do that, the data for all these galaxies piles on top of each other. And so there's something to do with basically the observed velocity is predictable from what Newton predicts, plus some boost factor, which is of course Mondy's formula. But you can show that empirically. These are just the data piled on top of each other without any reference to MOND. And the distribution here around that peak is narrow and completely explained by the known errors and what you expect for the scatter and the mass-to-light ratios of stars. We basically just assumed a constant mass-to-light ratio to make that plot. And it's still an incredibly small scatter. As Bob mentioned, that's not expected in dark matter. It was not predicted, and it's only after we told them the answer. Oh, yeah, we did that. Now, you can stretch this out to much larger scale. So here's the same data binned up, extended upwards through the solar system where everything is Newtonian. And of course, Newton was motivated by Kepler's laws for that particular thing. And now, Margaret Bauer and her collaborators have extended this to much lower accelerations of gravitational lensing. And so it really does look like there is one effective force law that governs things. That's one thing we need to understand. The big exception to this being clusters, which are all set here. This is a huge logarithmic scale. Right, so this doesn't look like a big deal, and maybe it's not, because again, astronomy, factor 2, big deal. On the other hand, yeah, it is a big deal. We don't understand that factor of 2. That's a real problem, and so John and Yingwei Li will talk about this, and I think Edwin, I assume, will talk about lensing. So this, all these different relations are not distinct in terms of this acceleration scale. They all show some acceleration scale. Federico Lelli has a nice review in Nature last year. And you can extract an acceleration scale independently from each of Pauly Fisher, the central density relation, the radial acceleration relation, and those logically don't have to be the same thing. So within the errors they are. And so I've gone through and measured the acceleration relation and the acceleration scale from these different methods. And it's always within 0.1 of 1.2 times 10 to the minus 10. Even going down to very low accelerations probed by the weak lensing data, with the exception of really low acceleration things where I'm not sure I trust the data. Okay, that is just a very brief overview of the data. What do we do with it? Of course, we have the scientific method where we emphasize the ability to predict things a priori, and that's what's supposed to keep us honest, right? Make a prediction ahead of time. And a theory is only good as its null hypothesis. If it doesn't give you something to test, it's not even really a theory. And unfortunately, when it comes to galaxy dynamics, that's often what we're doing with dark matter theory. So the gold standard, of course, is a prediction you make in advance. Now, a lot of times you don't really know, and so sometimes you can only say, oh yes, it has to work out like that. A good example of that historically is the precession of Mercury. Right? That problem had been known for many decades before Einstein invented general relativity. But when he worked it out, he was floored, basically. Whoa, this works out. Right? So that's I give that a silver star. Things you have to fit, sometimes that's good, sometimes it leaves you just making stuff up. There are other things. No theory addresses all phenomena. You should not write down a theory of everything that does everything all the time. So sometimes it's okay to say you don't know. I don't know what cosmology is in MOND. That's terrible. But it also doesn't address it. It's just beyond the scope. And other times, of course, it's wrong. And so a theory, to be considered a physical theory, has to be falsifiable. And this has driven me crazy. I've posed this question many times. What would falsify dark matter? Because people seem reluctant to consider MOND until they convince themselves that dark matter is wrong. But you can't actually do that. Now, what impressed me about MOND was that after I heard a talk by Mahdi, I went back and looked up his original paper, and at the time I was working on low surface brightness galaxies, and right in his paper, written over a decade before, was that galaxies with low surface brightness would provide particularly strong tests. And that's because they're way into the modified regime. Low surface density maps to low acceleration, and so that's important. There was no reason in the conventional dark matter context to expect that at the time, and in fact I did not. But here are a list of predictions that he explicitly made, all of which have been corroborated at this point. And the one I want to highlight is what really made me worry seriously about the dark matter problem. Right? Until this, I was perfectly conventional upbringing. I believed in dark matter like everyone else. But there is no dependence on surface brightness in the Tully-Fisher relation. So the different colors here are different bands of surface brightness, and I had explicitly predicted, right? I did have a null hypothesis. I had predicted for a dark matter galaxy formation theory that there would be a shift with the surface brightness from Tully-Fisher that is not observed. And I spent a lot of time trying to fix it, or fudge it as you like. And everything I tried didn't work. I could explain just about anything except what we were actually observing. And so nowadays I hear people explain this, but if they do this part right, they usually get the diversity of rotation curves wrong and vice versa. Can't do it all at once. Because you can't legitimately make a dark matter theory look like MOND, not satisfactorily, and that's what you need to do to make it look like the data. So here's the radial acceleration relation again, extended to low accelerations. These green lines are some ΛCDM models made by Ping-Fei Li, and they all turn away from here. Now, I've tried building a lot of models on here. Here's the residuals. You always got to look at the residuals because this is a log-log plot, so you can hide a lot of nonsense, right? They all look like the same line here. Here they start to segregate, and that seems to be generic. This is a good model. I've built lots of models. Most of them do worse than this. So usually you see in ΛCDM models some segregation by mass. No evidence for that in the data. And you see a turn down at some point. Now you can play around with the relation between stellar mass and tabular mass or whatever you're doing to modulate where that turn down happens. But it always happens because the outer parts of NFW halos have the density falling off as r to the minus 3. Whereas the slope of this line corresponds to r to the minus 2, i.e. a rotation curve that remains flat indefinitely out to almost megaparsec scale. So this is a generic failing of dark matter models. They do not explain this. It's easy to fool dark matter fits. This is just one example of another gas-rich galaxy, DDO 154. Particular paper, here's a dark matter fit. Woo, no problem. Here's the MOND fit by the same authors. Look, it's wrong. Okay, well, it's a little bit wrong. And the reason for that is that they did not allow, they didn't marginalize over the nuisance parameters. But basically, a one-segment tweak to the distance gives you a perfect fit with perfectly reasonable posteriors. And so, even when MOND is wrong, it's telling you something that you would never notice in terms of dark matter because you just fit the data. You have too many free parameters for what the data needs to fit that. It also, MOND, knowing about it, lets you know, do things that you just simply cannot do with dark matter models. So here's a model of the Milky Way I made just by fitting the terminal velocity data, this great data. Okay, that's a fitting exercise. It tells you what the corresponding mass distribution has to be. And that mass distribution has bumps and wiggles that correspond to where the actual spiral arms are going to be, just like you see in external spirals. So that lets you reconcile the Gaia rotation curve with these ISM velocities, otherwise in great tension. It lets you predict the outer slope, so that gray area was the only region that was fit. All those data came after. Perfectly well predicted. You can extrapolate it out, so you notice the change in scale here. This is what you expect at much larger radii. A bunch of halo star data out there, looks very good. And the model I had built for the inner regions, we knew the mass distribution of the bar. That predicts very well the data that were subsequently measured. So basically everything on this plot that's data, other than the gray stuff, came after the model. You cannot begin to do this with dark matter. In dark matter model, you say, okay, there's a halo, let's assume an exponential disk, and you start building things, and you never get this structure. You can never predict the slope. You just can't do it. Marty and I applied his formula to predict the velocity dispersions of the dwarf spheroidals of Andromeda as they were being discovered. So a decade ago, there was this big project called PANDAS that was identifying these dwarf satellites. And I realized that there was an opportunity to make an a priori prediction because they were finding these things. And okay, you told us this exists. I can use MOND to predict how fast the stars will move. And so we did it. And they were doing this so fast that they were sometimes publishing the velocity dispersions faster than we could write up the predictions. And so some of these are silver stars, but they were actual gold stars because we worked it out before we actually written it. And some of these were genuine gold stars. And so this is sort of what I mean by forest in the trees. This is the forest. MOND works over and over again. It gives you predictive power to actually tell you what the velocity dispersion is going to be. And, oh, this one's wrong. Whole thing, let's throw it out. Maybe that's the right answer, but you have to have something that does better. Or it could just be there's something weird going on, like we have the distance wrong with that. I'll note another thing here. Andromeda 4 is not a satellite of M31. It was thought to be when it was first discovered. Marty looked at the velocities and said, no, it's got to be a background object. It's too massive, it's too fast. And somebody later went out and measured a Cepheid distance, and sure enough, it was further away. So, you know, again, you just couldn't do that with dark matter. That's a prediction in my ΛCDM. I'm quite serious about that because there's no agreed way to actually make this prediction. One way you could attempt to do it is to look at one of these stellar mass-halo mass relations. You see a stellar mass, you have a corresponding halo mass, and that halo mass gives you a velocity dispersion. But this relation is highly nonlinear, and so there's a huge range of stellar mass corresponding to a narrow range of halo mass in this mass range. And so basically, the nominal prediction from that flavor of ΛCDM is that they should all be the same. But they're not. I can tell the difference just by looking at it. So MOND is the only theory where I can actually look at an object and predict what that object will be doing in the real world, not just some statistical statement about what's going on in a computer box. You just cannot correspond a simulated galaxy to some real world object. Crater 2 is another example. I'm running out of time, so I'll skip that. But I will note there are some non-equilibrium effects that were anticipated by Brada and Milgram all the way back in 2000. So I think Crater 2 is now, we know it's now had a close pericentric passage, so it's blowing up, and so its size is expanding. The velocity doesn't vary that quickly, so this trick still works. And it was surprising, very surprising from the dark matter context, where you should have had a lot of velocity for this big object, that its actual observed velocity dispersion is very low. That was predicted a priori by MOND. Clusters. Clusters, MOND does not do right. The mass budget is wrong. And I illustrate that here by extrapolating the Tully-Fisher relation. That line is MOND, so up into the cluster regime, there's a clear offset. Right? So the mass budget is just wrong. We've known that for a long time. And you notice the dashed line for lambda CDM, that intersects at the cluster scale, and that's what gives you the cluster baryon fraction being consistent within years with the cosmic baryon fraction. But note that's only true for the very most massive clusters. It's already wrong for 10 to the 14 solar mass clusters. And there are other things lambda CDM does not predict that MOND did, like the slope of the mass temperature relation. You notice these data are pretty much parallel to Tully-Fisher. So there's an offset. That's the mass normalization problem, is that the offset is there. But the slope is right. And that's not the slope that you expected in lambda CDM, that's this. And so when you hear people talking about preheating, that's basically, we want there to be some extra temperature to make up that difference. It's just something you have to make up to explain this failure of lambda CDM. The way in which things move is also wrong, though. We'll go into that. And so this is basically the fraction of detected baryons that you expect as a function of the baryonic mass of systems all the way from rich clusters down to tiny dwarfs. And in MOND is fine. It's basically what you see is what you get until you get to clusters. And so here's that discrepancy in MOND. Lambda CDM has an analogous discrepancy, just not in clusters, but in every other system in the universe. So does this falsify both theories? Maybe. But then what do you do? But what I really find, I have no patience with is people who only say, oh, this is a problem for MOND, we can forget it, and they're not even aware of this one. CMB2, this needs to be sorted out. I will leave that to smarter people. Constantinos is talking about this, I'm sure. And I will point out that I did predict the second peak right. Lambda CDM did not. Everybody who works on this thinks that lambda CDM got everything right from the get-go. That's not true. It got the position of the first peak right. People cared about the geometry, and that worked out. And putting on a cosmologist hat, I remember breathing a great sigh of relief when that happened, because in lambda CDM, which we had already established before these CMB observations, we were just assuming the geometry was flat. And I knew that didn't have to be true. So the big success of lambda CDM circa 2000 was the location of the first peak. That's neither here nor there to a test of MOND. The test of MOND is, do you have dark matter or do you not? And so this was the difference between those cases. And you can see that basically all the data are consistent with the case of no CDM for this ratio of the first to second peak. Because that's what lambda CDM predicted at the time. Now, it got the second to third peak right, but that's only after they'd broken the first to second peak. And what broke there was Big Bang nucleosynthesis, and that's a long story I won't bother you with. But basically, that is what we expected a priori. And we can fit this, but it is just a fit. And to do so, we had to change something fundamental that went into it. And once you do that, whatever. Finally, early galaxy formation and IMOs. This is what lambda CDM does predict for the mass assembly of galaxies. This is the size of this is the stellar mass looking back in time. So here's the main object assembling. Here are all the little pieces that feed into it. And you notice if you get back above 10 gigayears or so, these are tiny. There are no big galaxies at early times. You can see that visually in this cone looking back. The big dots are big galaxies. And again, a bit once you get above redshift 6 or so, there are no big dots left. Right? That's just corresponding to these things down here. Right? And so there are now lots of bright galaxies observed by JWST. These are data that existed entirely before JWST. This is a stellar mass, not of individual galaxies, but the characteristic mass of the Schechter fit to entire populations of galaxies as a function of redshift. or cosmic time along the bottom. And that dotted line, that is what ΛCDM models predict. That solid line is just what you get if you assemble an L-star galaxy at redshift 10 and let it evolve with an exponential of a tau of 1 billion years. And that's what the data follow. And Bob Sanders here predicted that in 1998. All right, so this was the prediction Bob made. Objects of galaxy mass will form by z equals 10. In 1998, he made that using MOND. That was an amazing accomplishment because at the time, that was complete crazy talk. Nothing should exist at 10. Was the contemporaneous statement from ΛCDM authors. Now, they didn't all write it down, but this one did. Momau and White's a touchstone in ΛCDM theory. Present-day disks were assembled as recently as z equals 1. So that's about here, which is right? That's where that line is. It's only just reaching its half mass at that point. This is a clear contradiction to the ΛCDM structure formation. We're still wrapping our heads around that as a community. I'm sure people will fudge it and do this and that, but there's an a priori prediction there. MOND got it right, ΛCDM got it wrong. And this is to do with structure formation, which is nominally what everybody says ΛCDM does better. Well, it doesn't. And so there's a more general problem, is that if you think about it, again, you need a prior, okay? Well, how does galaxy formation work? I don't know. But you put a bunch of baryons in a halo and you end up with something. Try it. You can come up with all sorts of things because there's a practically infinite number of combinations of disk and halo that can make something that might plausibly be a galaxy. So this big circle is meant to represent all the things that could possibly happen in a dark matter galaxy formation scenario. And then there's in MOND. There's one parameter, you know what the mass baryons are. That's it. There's exactly one thing that can happen. And somehow nature keeps plucking this needle out of the dark matter haystack. So I think the obvious inference is that this haystack isn't there. It's just that one needle is there. So I'll stop you with there, and I hope we have a lot more to talk about.
You do? Sorry, you do? We can't hear you without it. Just come in.
Stacy, you always talk with so many impressive diagrams. I wish I can make a talk like that. Some of them takes a little while to digest if you see them first time.
I cranked up the baud rate. I don't apologize.
I have to get back to you after the break. Just to, I don't want to go into the very details of it. I feel, it's only a personal thing, I feel there is somewhat of a, perhaps not so wise anti-dark matter feeling in just because we are in this room. I believe astronomy as everything is bottom up. So if there are things suggesting either way, we shouldn't just think of it as one or the other. As a theorist, I feel theory provides many possibilities and can be labeled by one word or one parameter. Etc. So I just like to encourage more thoughts to bring together the successes of two paradigms in their specific standpoint, but less of saying it's one or the other. Hence, it's clearly not just one. We know that with certainty in those simplistic form. Another very, very quick comment was even something so beautiful as Einstein's theory, in principle, allowed itself two parameters, capital G and a lambda. Einstein didn't fully understand the capital G, didn't fully understand the symbol lambda, And MOND was trying to do everything with a naught, of course borrowing a G. So, and standard theory was also like MOND, bottom up. There was no idea of quark at the beginning. Very, very bottom up. Took several a generation of bright physicists to arrive from things like, how collisions of, how neutrons become protons, etc. All these collisions, and took a long time for people to arrive at the fundamentals, which involve 20 so parameters, and it still looks said to be beautiful. We should not phrase MOND as a one-parameter universe.
Well, so I have a lot of sympathy with what you're saying about, I guess Young first made to me the analogy of the blind man and the elephant, right? We're all trying to figure out this greater truth, and maybe there are many ideas that contribute to that. On the other hand, I don't agree that it can't just be one or the other. I don't think it's right to say that it's dark matter and MOND. Those are very different branches of the tree, and a theory, if it's a theory, should be subject to falsification. And specific flavors of lambda CDM, realizations like the NFW halo, that's been falsified. Structure formation, that's subject to falsification. Yay. But just the generic idea of dark matter, there's some mass that's invisible. Well, sure, that's not falsified.
That's what I'm saying.
Yeah.
That's what I'm saying. That MOND is not saying what the matter composition is.
So we have to understand all these things. I absolutely agree with that. I've done more than I should have in 20 minutes.
As Oliver Müller here, a question. How many trees do you need to make a forest? Or in other words, how many galaxies, for example, do you need off the radar to say, okay, probably one is wrong, is falsified as well?
So I said 100 as a knee-jerk reaction because that was the threshold Rubin set for flat rotation curves. So basically, the first one she got, people were like, oh, well, that's just a weird case. And then she went out and showed it was true over and over and over again. And so we're well over that 100 mark with the wrong. But how many outliers can there be? Outliers are at the 10% level, and the thing is that the number of outliers is inversely proportional to the data quality. So what I have seen over and over again is that the data improves, they revert to the mean, which is defined by the wrong. Can I say that that will always happen every single time? I don't know, right? But I have not seen a case that is convincing. That's the
Thank you for such a nice talk. In the Fermi and McGaugh review, you mentioned 5 possible reasons for the mass discrepancy in the clusters. It's been a decade since then, and are you able to rule out any of those possibilities firmly?
This is a great dissatisfaction to me, is that I don't feel like we're any closer to understanding that. I don't think we can really exclude any of those possibilities. Normal neutrinos are really hard to maintain at this point, so that's almost experimentally excluded, almost. But none of them were ever satisfactory, and we're still in that same mess. I do not see a satisfactory way out of that. The name?
I'm Srikanth, sir.
Hi, Bill Ehrlich. I have a related question about the discrepancy with the clusters. I was curious, and I haven't thought through this mathematically, so I'm asking because I think you could certainly think through it better. Would there be any possibility of the clusters being larger, older objects that, with A naught being related to the Hubble constant, if the Hubble constant, is different, the Hubble tension was different at that early time, would that be a parameter that could help explain?
So I think in MOND the prediction is that clusters form sooner than they do in ΛCDM. I don't think that helps with this problem, not in a big way anyway. I also haven't seen any clear evidence that A0 evolves with redshift the way the Hubble constant.
Okay, thank you.
Hi, I'm Alfie Russell. I was just wondering, you mentioned this Sanders 1998, where the galaxies and MOND should form a redshift of 10. I was just wondering what, if you knew what kind of cosmology was used in that paper, and would it still be a realistic prediction to use with our modern understanding of cosmology?
So the cosmology at the time was just baryons only. The assumption was that on large scale, FRW still held. And so it was only the baryon of 0.02 to 0.04. You know, and you could or didn't have a lambda. That didn't really matter. Now that obviously does not fit the metric measures that we know about now. So it's not a viable cosmology in that respect. Neither is lambda CDM, right? Lambda CDM works if and only if the dark matter is a real physical substance. So I feel like what we're doing there is pounding a square peg into the wrong hole and inventing things until we assume FRLW now is right and invent whatever things we need to make it so. I think what MOND is telling us is that that probably is just the first approximation. And whatever grander theory there is going to give us a different cosmology, to which FRW is, of course, the first approximation, because they have to be using GRW. So I do not care if it's the right cosmology or not. What I think is robust and still holds is the time of that. Right? It's just basically how long does a galaxy mass take in MOND to expand, decouple, turn around, and collapse. It's very quick, and it's around that time. You know, the universe is expanding. We agree on that much. So that redshift is pretty robust, regardless of what you do with the cosmology.
Thank you.
Being sure to give you your exercise, asking questions from everyone.
Okay, I'm Ricardo Scarpa, just to mention my name for who doesn't know me. And speaking of this problem of cluster of galaxies that apparently do not agree with MOND, and you just said one important thing, that we all stick on the idea that the universe is expanding. But cluster of galaxies actually are the only structure that are so far away from us where cosmology is irrelevant. Cosmology does matter when you study clusters. You don't care about cosmology when you study rotation corrosion of galaxies, for instance. And that makes a huge difference. So why do we have to stick on lambda CDM when MOND is telling us that the CDM doesn't exist? On what are we sticking?
We don't have anything else to go to. That's the problem. We need a
Well,
theory that
I think we have alternatives. Actually, it is just in front of our eyes, and James Webb Space Telescope is actually destroying basically everything and producing a revolution, totally unexpected. I will talk about this tomorrow.
yeah, that's great. We definitely need a better theory. As far as JWST, not only is it showing that really big galaxies were already present at high redshift, it is inferred that they're very compact. That's strange, that you're packing a galaxy into a few hundred parsecs. And that suggests to me that we just have the angular diameter distance long. Yeah, so.
Where's this diagram pulled from? Where's this
I
diagram?
made this.
Okay, not
So-
published.
So the data, so I had a student, Jay Frank, graduated 5 years ago. He was 5 years ahead of his time. So most of the blue points up there are due to Jay. And they were from Spitzer data, not JWST. And he has a version of this in a paper we wrote in 2017. In that paper, it's M star, the luminosity evolution, and I've just translated it here into stellar mass. But so that luminosity version is in the literature.
Thank you very much.